Now, a corollary to the theorem that we had last time about Euler circuits will give us a characterization for when an Euler trail exists that is not a circuit. Remember, an Euler circuit is a special Euler trail, but the question is, when do you have an Euler trail? That is a trail then that uses every edge but doesn't return to the start. So I'll give an example of a graph down here that has that. The statement is that a connected graph of order 2 has an Euler trail that is not a circuit if and only if G has exactly 2 odd vertices and all the others are even then as a result, right? So again, we're just looking at graphs with at least 2 vertices. Doesn't make sense in another context. So here's an example that illustrates how the proof works. So here's a graph of a that has exactly 2 odd vertices. If you'll notice, if we tick through here, that one has degree 2, degree 2. Then the rest of them have 4, degree 4, degree 4, degree 4, degree 4. So they're all even except for these 2 up here that have degree 3. So it doesn't satisfy the theorem. Since it has odd degree vertices, it does not have an Euler circuit. No Euler circuit. But here's the thing, if we add one edge, so let's suppose we add one edge connecting the 2 vertices of odd degree, now this changes this to a 4, that changes this to a 4, and then every vertex is even, and there is an Euler circuit. So there is now an Euler circuit, adding the edge, adding I to A, allows an Euler circuit. In fact, we could even probably figure one out. Not sure if I want to do that. Yeah, I don't know. Let's see if we can do one here. See, an Euler circuit might do, let's go from A. Oops, let me get the highlighter. Oops, that went gone. All right, now let's go from A to B. Let's see if this will work out if we just consume these. And then if we go from A to F to E to D to C, then we have to go to A to D to F to I to A. We started at A and there's an Euler circuit, right? So the Euler circuit I wrote down there, it might be helpful to see it. The Euler circuit I wrote down there was A to B to C to E to G to H to I. I just went around the outside. And then I went down to G and up to F and down to E and up to D and down to C. And then I had to go, the only way I could go then is to go to A. And then from A I went down to D and over to F and up to I and then finally across to A. So notice what happens here. The one additional edge here, I actually had configured this so it'd come at the end just to see how this works out. If I go back now and remove that, gives us an Euler trail. So that would be tantamount to removing this guy right here. So now that's an Euler trail from A to I. Yep, and that's exactly the way it works in general. So in general, I'll go ahead and write this down real quickly in general. So proof. If G has exactly 2 odd vertices, add an edge connecting them. Okay, then an Euler circuit exists, and removing the edge we added one leaves and Euler Trail. And by the way, what happens is an Euler Trail goes from one odd vertex to the other. It starts at one and ends at the other. That's the way it must be. So that's how you can show that if you have exactly two odd vertices, then there is an Euler Trail, and that is not an Euler circuit. And it works exactly the same way the other way around. Suppose there's an Euler Trail that is not an Euler circuit, then the start and finish must be odd. An Euler Trail that is not a circuit must start and end anodond and end at an odd. Must start and end at odd vertices, so it'll be different ones, since it's not an Euler circuit. Right, so that's what's going on in the other direction. So if you have an Euler Trail that is not an Euler circuit, then it starts at one vertex and ends at another by adding an edge to the start and end. And Euler circuit results, just reversing what we did in the first case, first half, the first direction. So all vertices are then even, meaning the start and end, or initial and terminal vertices, were odd, but all others were even. Yep, so that's the if and only if. If it has two odd vertices, it has an Euler Trail that is not a circuit. And down here, if it has an Euler Trail that is not a circuit, then it has exactly two odd vertices. So where does this problem come from? The problem I mentioned with Euler, the Königsberg bridge problem. The Königsberg bridges over the Pregel River in Prussia, what is now part of Germany, in the town of Kaliningrad, the city of Kaliningrad now. The Königsberg bridges, Pregel River would look something like this, and in the Pregel River there was an island, and then a bigger land mass over here that I won't show all of. And so in here we've got water. That's water. That's supposed to be water. Yeah. And so on the from the shore, this is shore, and this is shore over here, there were bridges that connected the shore to the island, two from each of the sides here. This is inside of the town of the city of Königsberg. You can see pictures of it. If you look online, you can see a depiction of it. This island was connected to this other island in the middle, and then the shore to this island also had bridges like so. So the question was, can one take a walk and return to the start, where you started, crossing each bridge exactly once. So can you do that? Is this possible? And what Euler did was he said, well, you know, it doesn't really matter that this is this big landmass up here, you know. You could think of this as one thing, because if you can exit over here, you can certainly walk along that landmass and get over here if this is where you started, right? So there's no reason to consider this big shore as this landmass. We can think of it as one location. And the same for this landmass, so we can think of it as one location. And the same for this one, the same for this one. So there's 4 locations and bridges connecting them, and so he drew a graph to represent it. So this is the upper shore in my picture. This is the lower shore in the picture. This is the island, this island right here. And this is the other island, that island right there. And then there are 2 bridges connecting the shore to the island, 2 connecting the island to the other shore, 1 connecting the islands together, and 1 from the shore, the far shore, to the right-hand island, 1 from the near shore to that island there. And so this is a graph, and the question is, can you cross each edge exactly once and return to the start? Does this have an Euler circuit, is a way to phrase it. And the answer, because the degrees are all odd, no. It has vertices. It has odd vertices, the way we would say it, vertices of odd degree. In fact, it doesn't even have an Euler trail where you can start one place, cross them each, and end someplace else, because it has 4 odd vertices. So that's the Königsberg bridge problem in the context of Euler circuits.